got a car.
What, beg pardon?
You have a car.
Oh yeah, I know. I told people that I'm in. Veronica said you're not wearing sunblock. I said I don't need sunblock. So there's a big meeting here, ISBA meeting, general meeting for How was your? Did you had a position? Wonderful that you did the presidency. Really good. No. What a good guy.
Would like to do more. Back is his home. Back home.
Should I?
Where's your? Yeah, if someone asks you. 2 nights.
Should I say that too? Should I say that too? It's not good to. Okay, welcome to this lecture. Before we start, a few things. One is Christian Robert. Maybe you were not aware, but he was in the hospital for 2 nights, but now we know he's back out of the hospital in good spirits, and he may even show up later or not, I don't know, but he's fine in any case. The second thing I would like to do is to make a word of thanks to all the people who helped us out with setting up the rooms and the talks. Just like to say this was a wonderful organization, and like to thank you. Then we go to the talk, and I'd like to introduce our speaker. If I put my glasses, I can even read what I wrote. It's my great pleasure to introduce our last keynote speaker of this meeting, Johannes Schmidt-Hieber from the Universiteit Twente in the Netherlands. Johannes' research is characterized by the great depth of its investigation, where he typically chooses to work on mathematical questions that other people find beyond reach. Johannes' research is equally remarkable by its width. Johannes has tackled subjects from multi-scale methods to Lecam theory, from volatility estimation to non-parametric confidence statements, always making very essential and original innovations. In our Bayesian community, he's perhaps best known for the theoretical analysis of the spike and slab prior and posterior in high-dimensional regression models. His work not only justified these priors in certain situations, but also gave insight in importance of the various hyperparameters of the problem. More recently, Johannes started working on the very different subject, again, of deep learning. He's the leading expert in trying to understand, from a statistical perspective and through theoretical analysis, why deep learning methods are so effective. And today, he's presenting a Bayesian side and perspective on this line of research on deep Gaussian processes. Johannes, please.
Okay, so welcome. Thanks for this extremely nice introduction. I feel very grateful. And it's a huge honor to be here and to present my work. So to cheer you up after lunch, I thought I'd just ask ChatGPT to draw an image on how ChatGPT imagines a Bayesian conference in Venice, and that's what came up. So it's, I think it comes quite close to, but somehow the DALL-E, which underlies the image generation of the ChatGPT, imagines that we have maybe a bit more fancy lecture rooms, but otherwise I think it's quite close. So what I want to present today is some joint work. I will try to present a bit an overview about the theoretical work, but that mainly is based on these two papers. And this is with my collaborators. Gianluca was a PhD student with me and is now in Vienna as a postdoc, and then this Matteo Giordano, who is now in Torino, and Koyan Wei at Imperial in London. Okay, so what drives this research? As Art mentioned, I worked for a couple of years. I tried to understand a bit more from a statistical perspective how these deep neural networks can learn functions. And now, based on these results, you want then to see whether there are Bayesian methods that can do as well as these theoretical guarantees that we have for the deep neural networks. And that's also the way I want to present this research today. For the moment, I don't try or neglect or ignore a bit the question of whether these methods, these Bayesian methods, are computable or not. It's really about you try to get these theoretical guarantees. And that has happened before. I mean, there's also a certain tradition of approaching problems in that way also in computer science, but of course also in Bayesian statistics in the past. But I don't claim that this leads in the end to something that you can right away implement on your computer. Okay, so let me start with the setup that we consider. So throughout the whole talk, we will always consider non-parametric regression as a case for supervised learning. And in this non-parametric regression setup, we say that we assume we observe n IID pairs. So these inputs are d-dimensional, and we have real-valued outputs yi. And so they are modeled by this equation where we say that there's an unknown underlying regression function, f, that sends these xi's to the yi's, and then on top of that, these yi's are perturbed by measurement errors. And that's something we can feed, for instance, into a deep neural network and then see how well the deep neural network can learn this underlying function f from the data. But we can also use, of course, deep Gaussian processes for that. And so sometimes you will see this n, that's always the sample size, and that will occur in the convergence rates and also the posterior contraction rates. Okay, so that's the structure of my talk. Before I come to the deep Gaussian processes, I want to motivate the specific deep Gaussian process priors by the function class of compositional sparse function, which somehow naturally arises in the analysis of deep neural networks. And once we have introduced them, and based on that, so we design a deep Gaussian process priors, we will show some posterior contraction rates. And I want to show that Gaussian process priors can't achieve this posterior contraction rate, that there's really something that deep Gaussian processes can do, which Gaussian processes cannot do. And at the end, I want to look briefly at some recent results about deep Bayesian neural networks. Okay, so let's start with the compositional sparse functions. And if you have seen talks by me before, that is how I always start. So if you have seen it before, I'm sorry, but I think it's important. A deep neural network, if you wonder what can it do, what other methods cannot do, well then the way it's built on stacking layers on top of each other, and then you can immediately guess from that somehow the way it's constructed should maybe be a natural class of functions that it can easily learn are functions that themselves are compositions in some way. Okay, so because it has this compositional structure, so it should be able to pick up compositional structure in functions that it learns. Of course, these compositional structures don't have to look like neural networks themselves, so they can be a bit more abstract, but it should be able to do that. And that is one possibility, and of course there can be many other possibilities where deep neural network somehow do better than other existing methods. But it's also a bit in line what people observed, that for simple classification tasks, for instance, the deep neural networks are not better than random forests, so sometimes one wins, sometimes the other wins. Only if you have something very complex, so then these deep neural networks tend to be significantly better than other methods. Okay, so what is a composition of functions? Here's an example. So for instance, suppose the function that we want to learn is itself can be represented in this form. So it has some G1, G2, G3, like inner functions if you want, and then this outer function H. And so why is that somehow helpful to such a representation for learning the function f? Because the hardness of the estimation problem is driven to a certain extent by the number of input variables. So there's also this curse of dimensionality phenomenon that says the more input variables you have, the harder the problem gets. But if you have such a compositional structure now, if here every function in this compositional structure only depends on at most 3 variables. They're somehow connected to each other, but these individual functions should be easier to learn than the function f, and then maybe also the composition is easier to learn than the function f. And to each of these compositional structures, it will be convenient to associate such a graphical representation. So I will always refer to the compositional structure as a graph, and that somehow here you see like these functions on which variables they depend on. And so here, like every node has at most an integrity of 3, so that this corresponds to the dimension of the variables on which they are defined on. Okay, so in practice, is that a good assumption? Are these compositional functions really occurring in the real world? And is that something which we can see somewhere? And I think people are more and more ready to believe that. It's very hard, of course, to test that, whether that is really the case or not. But there are many ideas on, indeed, that certain things that are where the input-output relationship itself has some intermediate steps, that then the function is a composition. Okay, so one way to maybe motivate that is to think about if the inputs somehow cause the outputs, but not directly, but by some intermediate steps. So think about, for instance, the smoking causing cancer. So it's not going that smoking directly causes cancer, but there's many intermediate steps. So if you just look at this as input and output, then you don't see that, of course, but if you really, try to discover the whole pathway on how that works, then you see that there are intermediate things in between. And in this graph, which I took from a paper, so you see that not everything is connected with anything, right? There's some sort of sparsity in this graph. And that's exactly the thing that is quite characteristic for all these ideas on how compositions in practice look like. Okay, so that's an example. Now about compositions. By composing functions, you can, with simple functions, you can create easily very, very complex functions. Yeah, so we all know fractals, which are typically based on a simple operation or transformation, which you iterate over and over again, and even after a few iterations, you see very complex shapes occurring. That's one example. Another example of how you can build from univariate functions, multivariate functions is the so-called Kolmogorov-Arnold representation theorem that says that any function in d variables, any continuous function in d variables, can be exactly, not approximately, but really exactly be represented by a composition of univariate functions. Yeah? So if you don't, I mean, univariate functions is much less than multivariate functions, right? With multivariate functions, all sorts of interactions that you can have between the variables. But if you allow for compositions of univariate functions, then this is rich enough to represent all the continuous functions, the multivariate continuous functions. And that has to do with the fact that so that the argument relies on space-filling curves. So if you invert a space-filling curve, then you can write it as a sort of additive, in an additive form, and that's all based on univariate functions. And then if you allow compositions, then you can represent multivariate functions in that way. So you see that just one composition already makes it much, much more rich, the space of functions that you can express. And another phenomenon, if you compose functions, is that if you compose several functions, then you can decrease the smoothness, so it can become these functions can become much rougher objects, and that's also important for this talk here. So here I have an illustration. If you take a Brownian motion, and Brownian motion is known to have Hilbert smoothness almost a half, and then if you compose a Brownian motion with a Brownian motion, then you get, I mean, if you take the same Brownian motion, then it's iterated Brownian motion. But in any case, the smoothness of this composition will have smoothness which is a quarter, which is exactly a half times a half. Yeah? So you see that these smoothness indices, in this case, they multiply. And it's something which we also see back in a second. So you get a much rougher object by composing functions in some cases. There are, of course, also cases where compositions are but not that useful. I mean, for instance, you compose with the identity function and nothing is going to happen. In particular, if you compose somehow with Lipschitz functions, then you always stay within Lipschitz functions. So, of course, maybe the Lipschitz constant can go up, but if you say you only compose with Lipschitz 1 functions, then you can't increase the function space by compositions or so. So there's also it can also happen, of course, that compositions are not doesn't give you anything new here. And so it's very hard to, I mean, there are very different directions that compositions can take. Okay, so now let's come to this function class that we introduced to analyze deep neural networks and show the power of deep neural networks. So we have seen before also in this example of smoking causing cancer, and so that there are underlying graphs when they are sparsely connected. And if we translate that now into function spaces, then we will say now that a function is compositionally sparse if it can be written as, where's my pointer? Somehow gone. Okay, if it can be written as a composition of, say, q plus 1 functions, g0 to gq, and these functions, each of them can map from some Euclidean space to another Euclidean space with a different dimension. That's not so important. So they're vector-valued functions. We assume that all the component functions have the same smoothness for a given I, so there's a smoothness beta I associated with it, say Hilbert smoothness in this case. And the crucial bit in this function space is that each of these component functions is say, restricted or constrained only to take ti of the possible di variables. Okay, so all of these di variables can go in some component function, but every component function can only take ti variables. So that's really what drives, in the end, the rate. That is somehow that you constrain, if you think about this again as a graph, where you constrain the edge degrees with that constraint. So this is the important quantity, these ti's. And then we also have the beta I stars. So we have smoothness beta I that is put on the gi, function gi. But then I said by composing functions, for instance, with these Brownian motions, you can multiply so you can decrease the smoothness, and that can happen. So what for non-parametric regression is important is somehow that you discriminate between the smoothness of the noise, and which has very little smoothness compared to the smoothness of the signal, the function. So it's about what really drives the rate is at the end not the smoothness on the gi's, but the induced smoothness on the f. And so what happens here is that the effective smoothness is not the beta I, but beta I and then multiplied with this factor where you see that whenever you have smoothness indices that come later in this composition and that are smaller than 1, then this decreases your effective smoothness in the end. Okay, so we get these beta I stars. And then in this, we said we always work in the non-parametric regression model. And in this non-parametric regression model, the minimax estimation rate is then only described by the beta I stars and the ti's. So it has this form. In the classical non-parametric regression model, where we just put smoothness on the f, we get n to the minus 2 beta over 2 beta plus d, where beta is the smoothness on the regression function f, and d is the dimension. And now it's all in terms of these effective smoothness indices, beta I star and the ti, which I introduced earlier, and it's the worst case over all of these possibilities. So it goes the maximum from I from 0 to q. And the result that I worked on earlier is to show that deep value networks, if you take sparsely connected neural networks and do all sorts of tuning and look at empirical risk minimizers and so on, then they can achieve this rate of convergence. And so they are minimax optimal. What is also important is that, okay, maybe what I do is first I think there's the battery is gone, so someone can help me. It's not going to move, and also the pointer is not. Yeah. Okay, good. Yeah. So then I change here the slide. Okay, so here's maybe the most important example of compositional structure are generalized additive models, because they very much also resemble the structure of this, which underlies the Kolmogorov-Arnold representation theorem. So here we assume that the function that we want to learn, called f0, is composed of univariate functions, and it has the summation in between. And then you can write that f0, you can write it as a composition of 3 functions, g0, g1, and g2. And okay, so there's some mistakes at g0, g1, and g2, and not g1, g2, g3. So g0 just maps to the component functions. And so in this case, the t1 or t0 is 1, because any component function just depends on one variable. This G2 is doing the summation, and the summation is a smooth map. So it's a high-dimensional function, but it's a smooth map. And then finally, the G3 is the representing the outer function, which again just depends on one variable. So this G3 is equal to 1, and then you can work out, based on this formula on the previous slide, what the convergence rate is. And the convergence rate is then n to the minus 1/3 that can be attained by deep value networks under all these conditions that I mentioned before. Okay, so that's one example, and there are many other examples of known constraints which can be put into this general framework of sparse compositional structures. Interestingly, if one looks at wavelet thresholding estimators, which are known to work well for many, many non-parametric estimation problems, but they are, in a way, they look at the linear expansion of the function space, and then they have problems with structures like that. So if you just look at the size of the wavelet coefficients, then you cannot really discriminate between that and an ordinary d-variate function. And so what one can show is that wavelet thresholding, if you define the method in a specific way, then it cannot achieve a rate that is faster than n to the minus 1 over 2 plus d, which is always, if d is larger than 1, this is always a smaller rate than the rate that value networks can attain. So it even has this curse of dimensionality in there, such that if d becomes very large, then this will decrease the rate, whereas this rate remains stable and the d only goes into the constant but not in the convergence rate. Okay, so this is how to go up. Okay, thank you. So just to complete that is now, there's this recent paper from Tommaso Posterior, one of the great Italian machine learners. And he says, basically in his paper, he starts the paper by saying that compositional sparsity of the target function, the function you want to learn, this is somehow the key principle underlying machine learning. That I see it rather as one possible mechanism, but it's definitely an important thing to look at. Okay, now to summarize that part about compositional sparsity, I want to argue that it's somehow a natural function class. It comprises a lot of other things like additive models or generalized additive models that we looked at before, but it's more general. It also can basically capture these manifold learning problems and many others. And the deep neural networks, they can achieve good rates for these problems. Now, the thing is that we now would like, of course, to see whether we can somehow tune deep Gaussian processes in such a way that they can learn these compositional sparse function classes with similar convergence properties as deep neural networks. And to look at this, what are deep Gaussian processes? Well, probably you all know this. So they're different, it's loosely defined as processes that somehow have a hierarchical construction which involves Gaussian processes. They're around for already a couple of years. Here in my talk, I think about deep Gaussian processes as really composition of Gaussian processes, but it can be many other ways. You can also just take as the mean function of a Gaussian process a different Gaussian process or something else, right? So there are many other things you can do, but here really I want to think about them as composition of Gaussian processes. Now, suppose we believe that these compositional sparse functions are great function classes that we would like to be able to learn with our Bayesian methods. So how should we set up a prior then? Well, one option would be, of course, just to say, okay, we set up the prior by just composing Gaussian processes with each other, but that probably will be not powerful enough to really learn this compositional sparsity. So rather what I want to do here is to do a hierarchical construction where in the first step of the prior construction, we put a hyperprior on these possible compositional graph structures, right? We think about compositions also as graphs. So we put a hyperprior on these graph structures. And then once we have the hyperprior on the graph structures, later once we have a graph, we put a Gaussian process prior on each of these graphs. And that will also involve some form of regularization that we have to do here, which I will come to later. Okay, so in the first step of the construction, we have all these. We want to charge all possible compositional structures represented, say, by graphs. For instance, these two ones here. And then, of course, it's a model selection problem. You all know this. That if you take a larger graph, then it's easier to represent your function, and so somehow you have to penalize that. So you have to find a way to put weights on these graphs such that you don't start to do overfitting with your deep Gaussian process prior in the end. And for that, so the weighting procedure is quite complicated, and I didn't put it here. I don't want to throw too many formulas here. You can look it up in the paper. So it really depends on all sorts of other things, like also the contraction rate that will show up only in a couple of slides. And so it's really, I think from the analysis, we get the impression that the weighting is extremely brittle, and it's all very sensitive to this weighting. So it's a bit like what we also experience in deep learning, and so that the tuning of the deep learning, everything is very, sometimes you tune it a little bit different, and suddenly it works much better. And so here we see also a lot of instability towards the way on how this is weighted, and has to be done very, very carefully. So that's an important thing. And so the way to do that, of course, again, is a hierarchical construction, where in the first step we think about these graphs as also layered graphs. So we put first a hyperprior on the number of layers. Once we have done that, we put a hyperprior on the width in each layer. So how many nodes do we have in each of these layers? And once we have done that, in the last step, we take a prior where we select which of these edges are active and which are not active. For instance, from X4, there's no edge that goes to G03. So we always think about a feed-forward structure, but still then, because we want to have a sparse graph, right? It's compositional sparse functions, they correspond to sparse graphs. So we have a prior that selects which of these edges are active. Okay, so that's how it then works. Okay, so once we have put up this model selection prior on the graph, so the next thing is then to put a prior on the corresponding function class for this compositional sparsity structure. And so ideally what you would like to do is you just put to every edge that is in the graph, you put a Gaussian process, which is of the right dimension. But the thing is, here, when we try to analyze that, the fact that we compose functions, which I mentioned before, can lead to very unexpected behaviors. And so think about this Kolmogorov-Arnold representation theorem property or so, that you can get very wild behavior by composing these processes with each other. And that is important because also for posterior analysis, this frequentist posterior analysis, even sets that get very little prior mass, they can somehow have an influence on the behavior of the posterior. Yeah, so that's always related to these small ball probabilities. And if you have somehow something which rather has a small prior mass, but still somehow it can show up and affect the posterior. So after playing around for a long, long time with that, being stuck at this problem, what we started to think about, okay, is in these compositional structures, we should also regularize the path behavior. We should take out paths that are lead to wild things. For instance, paths which, right, with a small probability, a Brownian motion can go very, very far from 0 to 1, right? But still that can have an impact on the posterior. And so two things which we do is to regularize that as we condition the paths to be in -1 and 1, and also we condition the paths to lie somehow close to some Hilda functions. So for instance, the Brownian motion or so that generates typically paths that are close to Hilda 1/2. And so then this conditioning doesn't really matter, but for other things, if you, it sometimes can have an effect. Okay, so once we do that, we got rid of all the problems. But the question is, and that's the thing I want to discuss here a bit, is that conditioning now really important or not? And I think one can again make a link to the deep neural networks, because in deep neural networks, you also have this problem that you can, by composing functions, that you can get very wild behavior. Yeah, so since they only think about the algorithm, so then they observe that by an exploding gradient or a gradient that is close to 0 and then it's not going to update anymore or so. So they, in their world, they have to keep the gradient always at a certain level such that it works. And so they have all sorts of regularizing mechanisms built into the deep learning that makes the gradient to remain stable over time. And so one thing is, for instance, the batch normalization, where you say, okay, I look and I write here down, the computer scientists wouldn't do that like that, but I write like down the sort of population version of that. So you look at what is the distribution of my outputs after a certain level, layer, say the ith layer, and then you renormalize that, you subtract the mean from that and divide by the standard deviation, and that is the signal that you then propagate to the next layer. Okay, so and that is another form of regularizing the functions that you get. It's based on the data, it involves the x, and as a full Bayesian, of course, we can't do something based on the data. The only way we can regularize is by changing the prior, by, for instance, conditioning on more regular sample path behavior. And that's what we do here. Okay, so now let's come to the theory. So what I do here is following this great work on non-parametric base to derive the posterior contraction rate, and posterior contraction rate as a concept from frequentist base. So you look at the Bayesian method, if a frequentist would use it, assuming that data were generated from one fixed regression function f0, and the posterior should see that, and it should concentrate around the f0. It should have all its prior posterior mass near the f0. And we say epsilon n is a contraction rate if asymptotically it covers all the ball around f0 with radius epsilon n covers all the posterior mass asymptotically. Okay, so that means it's like the radius of the ball around f0 at which the posterior shrinks. And there's a lot of great work. For instance, Vaart has some amazing work on that, where this is reduced to certain properties of the prior and the function class. And one important thing is here to notice that these posterior contraction rates, you can never be faster than the estimation rates, because from the posterior contraction, you can basically get a frequentist estimator with this rate epsilon n. And so that means the thing is a good, if you like, from a frequentist perspective, a good posterior would be one where the epsilon n is exactly this frequentist minimax estimation rate. Yeah? Okay. And then there's a specific theory for Gaussian processes. Gaussian processes have more structure, and in this case, one can relate it to other properties of the prior. And so the theory for that is developed in this paper by van der Vaart and van Santen in 2008. And it's an absolute highlight. It's so one of my favorite picks in mathematical statistics. I think it's one of the best papers that we have. And the question is now, for deep Gaussian processes, can we just rely on this result? The thing is, indeed, yeah, so it's more complicated than that because of the compositions of the Gaussian processes, but also because we have an underlying model selection prior that we put first on these compositional structures. So one has really to work hard to extend this framework, and there's all sorts of things, and that's also why this regularization of the sample path, and so that occurs because of this extra work that has to be put on top of the existing theory for posterior contraction of GP priors. Okay, so now the theorem is a bit like more what you expected. So it says that if you do all the tuning right and do the conditioning right, and so then these deep Gaussian process priors, they can get the optimal contraction rate for these compositional sparse function classes, which is the same thing we have seen before. So it's in the sample size, it's this rate which depends on these effective smoothness indices and the TIs. Okay, so that's a positive result, and it says somehow these Gaussian processes are able to do it, and for this hierarchical prior that I presented. Okay, so this the thing I want to reserve one slide to the computational aspect. So, of course, it's very, very hard to do that. I'm aware of that. And still, I think it's, in terms of the idea, it's interesting. And so one thing which is obvious is that in practice, you might not want to charge all possible compositional graphs. There are some which are more important than others. for instance, the one that corresponds to the generalized additive models. I think you always want to include it, but then some of them are very similar. I also mentioned that sometimes compositions don't add anything or very little, for instance, compositions of Lipschitz functions or so, and all this can basically go out. So in the end, we believe that you just should find a good empirical rule to charge compositional graphs that are sufficient different and that also lead to fast rates. I mean, if you anyways just get a slow rate over this compositional graph, so then there's no chance to recover this function, so then you can also drop it out beforehand. So typically, I think there will be a few small graphs that you should chart and then build your deep Gaussian process prior on that. But I don't think that theory can help you so much on really figuring out what you have to do. I think that probably would require also more empirical work. Okay, so I want also to mention another great follow-up work on that is the deep horseshoe priors that were promoted by Ismail and Thibault. They just had a paper on RKF on that 3 months ago. And so here, they can circumvent certain things that we had before. So we had to put a prior on which edges to include. But by using here a model selection prior and in this case the horseshoe prior from that has been used before for sparse signals, and then you scale your Gaussian process with this horseshoe prior, and that will make has a lot of mass near zero. So in this case, that means the process will not move at all. So you will not see, you have no effect. It's like as having no edge. And with a certain probability, you will see let's say the path here. And so that circumvents, by building in the horseshoe, that circumvents the prior on the edges and makes it already much simpler, I believe. Interestingly, they also don't need any regularization of the sample path. It's just enough to map them to -1,1, such that you can't get very large sample paths. But one difference in their analysis to ours is that they analyzed the so-called row posteriors. And row posteriors are where you take the likelihood to a power which is smaller than 1. And that has as an effect that this posterior contraction theory, you can get rid of one condition that causes a lot of trouble in our case, because that also causes all the conditioning. It says somehow that the posterior mass of a small set some vanishes, and then you don't have it anymore. And therefore they can come up with weaker conditions. And it's very interesting, and so because you can go with the row as close as you want to the 1, and suddenly once you go to the 1, you get a sort of different behavior, and you get or at least you get another condition in there in order to establish posterior contraction rates. But if you work with row posteriors, then you can get rid of this thing on regularizing the sample path. Oh, it's very nice work. So that's on the positive side. Now I want, in the next part of my talk, I briefly want to talk about lower bounds for Gaussian processes, right? Before we had upper bounds for deep Gaussian processes, and now I want to show that Gaussian processes are not powerful enough to learn these compositional sparse functions with the fastest possible contraction rate over all posteriors. Okay? So how does that work? Here's directly the result that says that if you just take a Gaussian prior, and now we consider, because we work on a lower bound, we don't have to consider all compositional structures, we just consider the generalized additive models, which are a specific case in which we have seen before. The generalized additive models, they lead to the optimal rate and to the -1/3, which is obtained by deep neural networks. It's obtained, as we have seen, by deep Gaussian processes, but one can show that whatever your Gaussian process is, the contraction rate will be something which is of a larger order than n to the -1/3 if the dimension is larger than 3, or larger or equal 3. And there is some sort of polynomial gap in the rate. It's not very large because in the most extreme case, if d goes to infinity, you get n to the minus 1/4 here in the lower bound, whereas we know the optimal rate is n to the minus 1/3. But still, there's some sort of polynomial gap in the rate. And it's different than what we have hoped for. We hoped for to get a lower bound that shows that Gaussian processes will always suffer from this curse of dimensionality effect, but we couldn't establish that. Okay, so because here, this thing is, if you take d to infinity, so it remains stable, it's not going to, the rate is not going to 0 or so, so you get stuck at the n to the minus 1/4. We could not remove that. And we worked a lot, so we worked out two completely different proofs, but both proofs, they lead to exactly the same lower bounds. And one of them has this nice inequality in here because I thought I wanted to show a bit of something technical. So how does it work? Because you have a Gaussian prior now. We work on a lower bound for Gaussian prior. So then it's enough to study the posterior mean, because if you know that the posterior mean is far away from the true function, then the whole posterior will be far away, or the posterior mass will be far away from the true function. And so the lower bound is as follows. It says if f bar is a posterior mean, and then under these different distributions, so that's the expectation, given that the true regression function is fj, we can show that this is lower bounded by that quantity where these f's have to be orthogonal functions. Okay, we also have a generalization for non-orthogonal functions, but the thing is now that you have to find suitable orthogonal functions to make this right-hand side large, and that gives you then a lower bound for the posterior mean, and that can be translated, and there's also papers by Sergius and Sven Wang, and so that can be then translated into lower bounds for the whole posterior. Okay, so that's one of the strategies that we follow. We also have, for specific priors, we can get stronger lower bounds. So people in practice have been using, for instance, these Gaussian wavelet priors or series priors in more general form. So if we think about a Gaussian wavelet prior, so then we say our function f can be expanded into a random wavelet series. So the psi, gamma, those are the wavelet functions from the wavelet basis. And then there are some lambda coefficients, lambda, gamma, that we can pick. And these psi, gammas, they are standard normal. And if we take that as a prior measure, then we can show that whatever the sequence of priors is and whatever these psi gammas are, we get always a lower bound, which indeed has this curse of dimensionality, because now the lower bound is -1/2 plus d. So if d goes to infinity, this rate becomes arbitrarily bad. And so you get very, very slow behavior. Okay, so that shows that for this class of priors, you indeed have a lower bound that has curse of dimensionality and is much weaker than what you get with the deep Gaussian processes. So it's interesting to see that there's a gap. And so this is what I want to now do in the final part of my talk. Just check. I want to argue that there indeed might be some sort of gap here. And so for that, I want to talk briefly about these deep Bayesian neural networks, which form another class of Gaussian processes. And what I want to argue is that these Bayesian neural networks, although they don't have anything explicit built in to learn compositional functions, they still bias the posterior towards compositional functions, that there's some implicit regularization towards compositional functions. Okay, let's see that. So what's a Bayesian neural network? You probably all know this. So you take a neural network and then so you can write a neural network in that form, right? And then those are matrices, weight matrices, and every entry of the weight matrix is sampled independently from the same distribution, say a uniform distribution or a normal distribution. And then in the wide limits, you can, if you do that, wide limit means you take the layers very wide, then what you do here is you basically generate a Gaussian process. But because you have somehow a very unusual way of parameterizing your Gaussian process with this layered structure, you can still get different behavior than with, say, series priors or so. And that is something which we will see later. Also, these objects occur for initialization and deep learning. So if you initialize your deep learning, then you also draw your weights independently, and basically you draw them from like this standard ways on initializing SGD for deep learning also does basically the same thing. Great. Okay, so that's a Bayesian neural network. It's a neural network, and then you put a distribution on the weights. And now the claim is what I said before, is what I want to indicate here, and it's still very vague, and it's not but still that these Bayesian neural networks, they have some sort of implicit regularization towards compositional function, although this is never put there explicitly via a hyperprior or so. Okay, so before I come to that, so which type of Gaussian processes do you get from that? Well, if we take a shallow network, which is a network with just one hidden layer, say of this form, you make the hidden layer very, very wide, and you put the variances of your prior of the right order such that it doesn't explode or be zero. Then you get, as a limiting object, you get a Gaussian process with this covariance structure. And so this is the activation function here, the sigma, and the W is the distribution of one row in your weight matrix. Yeah, so they're all ILD, so that means all these rows have the same distribution, and you just take here the expectation with respect to the distribution of the W. So that gives you the kernel, the covariance kernel of the Gaussian process to which you converge. And that depends, for instance, on the activation function. Okay, now if you take deep neural networks and make them very, very wide, so you might think, okay, then I get a deep Gaussian process, and that is not true. So you still get a Gaussian process. If you take all the width of the layers, if you take them at the same speed to infinity. Okay, so then you can use a CRT for exchangeable sequences to show that this process is still a Gaussian process, and the covariance structure has a sort of recursive formula which is based on this on the shallow case. So this was the shallow case here, and then there's a sort of recursive formula on what the covariance structure is of the deep Bayesian neural network in the wide limit. So how can we get deep Gaussian processes from that construction? For that, we would have to build in so-called bottleneck layers. So you don't take all the layers to infinity, so you keep some of the layers at a fixed size, and then you get, indeed, as a limiting object, a deep Gaussian process, or composition of Gaussian processes more specifically. And so here's an example to illustrate that, right? You can write, if you connect, I mean, you think about this node as two different nodes, then this neural network can be split into two shallow networks, right? And then if we make this layer very wide and this layer very wide, then we know this shallow network will converge to Gaussian process if properly scaled, and this one will converge to Gaussian process, and that's just the composition of these two. So this will converge then to a composition of Gaussian processes, and in this sense, a deep Gaussian process. So you can also get them. There's a lot of work now on telescope neural networks which have this structure, and some people understand that putting these bottlenecks in there has an important effect. Okay, so here comes the argument why these Bayesian neural networks should bias towards compositional structure. And to make this argument, I just want to look at the simplest case that you can imagine. This is linear neural network, so the activation function is just a linear function, so that means it drops out here, right? So this is just, you represent a linear map by a product of these weight matrices. It's completely over-parameterized, of course. And now, if we take, as a prior, if we take standard Gaussians, or let's say Gaussians with variance sigma squared, centered Gaussians with variance sigma squared on all these parameters, individual parameters, then, and now only look not at the full posterior, but just at the map, then the map is a minimizer of this the functional here, right? So the log likelihood will depend just on the product of the matrices. We don't really need to work it out what it is here. It's just important to see that's the product. And then we have from the Gaussian, we get in the exponent that term, right? We look at everything negative in the argument, so we get from a plus here, the sigma squared over here, and here we get the squared Frobenius norm of all these matrices, right? So we take, it's like if you square all the parameters and add them together, and then if we think about matrices, this is the squared Frobenius norm, right? So it's just the square of all the entries summed up. Now this one can be rewritten. This can be rewritten as a minimizer over just the product, right? So we are just interested in which matrix A do we get out, because that's all what matters for the prediction. It's not the individual weight matrices, but just the product of them. And if you then work it out for the product, you see that, you know, for whenever you keep that fixed, you can minimize over that term. There are many different ways. So that implies a penalization on the A's. And the penalty here is a so-called Sutton P norm. It's also a quasi-norm, because here you see that the P, that will decrease with the number of layers. Capital L is the number of layers. If you have one layer, then you get, of course, it's the same thing as here, so you would get the Sutton 2 norm. If you have 2 layers, you get Sutton 1 norm, and then afterwards you get to something which is smaller than 1. And so then it's not a norm anymore, just a quasi-norm. And so what is the Sutton P norm, or quasi-norm? It's just a P quasi-norm on the singular values. And if you go below 1, then you promote sparsity, so on this matrix. And so if you promote sparsity on the singular values of this matrix, then that will make this matrix A to become force that to become close or exactly a low-rank matrix. Yeah? And the larger the L, the more low-rank it likes to be. And so now what's the thing about this? Well, if A is a low-rank matrix, okay, so we had this thing, and then we see, so we can in principle factorize that as U times V, where this inner dimension is exactly the rank of the A, of the matrix A. And you can view this in principle as a compositional structure. It's not very interesting because it's just a composition of two linear maps. But then you already can imagine, okay, maybe that also holds in more general cases. If we, now we just looked at the linear neural networks. Okay, so if we put here an activation function, then of course you get much more interesting objects out of that. Maybe that's also true. And there was a recent paper by Arthur Jacot which showed that if you take deep value networks, so he considers in more generally piecewise linear activation functions, then this Gaussian process, the Gaussian process that you generate with, right, in the wide limit, this is also a Gaussian process here. This Gaussian process will forces or biases towards functions that are themselves compositions. And here, in this case, because you take an piecewise linear activation function, this H and Z, they're also piecewise linear. And the inner dimension, which before was the rank, is now a number that decreases to 1 as the number of layers increases to infinity. Okay, so that means, although we haven't specified anything on compositional structure in here, just we take a Gaussian process and parameterize it in that way of a deep Bayesian neural network, and that already is enough to make the posterior probably, or at least here it's the map, try to bias it towards learning compositional functions. Now, this is sort of related to all these other things on implicit regularization, and so on. The question is always, is that implicit regularization strong enough? We have lower bounds for, right? Before I derived lower bounds for Gaussian processes, which show that there is a polynomial gap between Gaussian processes and deep Gaussian processes. So they never can achieve the optimal weights for, say, the generalized additive functions or so. But there's a good hope, at least, that, for instance, priors of this form, they could at least achieve faster posterior contraction rates than, say, the wavelet series priors, because they have some sort of bias towards compositional structures, and they might see this this compositional structure better than the say, series expansion priors. Okay, so that's a bit open here, but this shows, I think now, to finish my talk, I try to give you a bit of overview about the topic. So we started with these hierarchical deep Gaussian processes where you put the hierarchical assumption in the hyperprior, and then you can show, okay, under all these conditions that I mentioned, you can get the optimal posterior contraction rate, and then for the full posterior, and there's this great work by Ismail and Thibault on deep horseshoe, GP's very recent work, and they can get rid of some assumptions for the row posterior, and they put the horseshoe prior to get rid of one of the hyperpriors that we had. And then they also achieved the optimal rate for these compositional sparse classes. For Gaussian processes, we know that there are lower bounds, and the lower bounds are, for general Gaussian processes, they're not very strong. For wavelet basis, they are very strong in the sense that they show some curse of dimensionality effect, which can't be circumvented by wavelet priors. And that's also for the full posterior. And then in the end, I wanted to motivate that there are very specific Gaussian processes induced by these Bayesian neural networks that somehow have built in this sort of implicit regularization towards compositional functions. And for that, yeah, it's completely open on which side they are. Are they more on the side of the series priors, or are they more closely related to the lower bounds that we have for general priors, general Gaussian priors? That's quite unclear, and that's an open problem. And with this, I would like to close, and this is the summary of my talk. Thank you very much.
Thank you very much for this intriguing talk. The floor is open for questions. Yes? Yep.
Hi. I'm going to ask a slightly, actually maybe very slightly provocative question, which is that in the results that you presented, the focus is very heavily on posterior contraction analysis through minimax properties, which are asymptotic. One of the things we know about such minimax properties is that, at least in the Gaussian process setting, is that they can't detect geometry. So if you consider a Gaussian process defined on a manifold and one defined on an embedded Euclidean space, and you kind of match smoothness appropriately, then the contraction rates you get are the same, in spite of the fact that one of those models, you know, is much better than the other in practice. And I'm wondering if you expect similar kind of phenomena in sort of this much more neural network kind of setting, where do you think we can, even in principle, detect kind of differences in behavior through sort of asymptotic rather than finite end analyses?
Okay, yeah, thank you for the question. Indeed, yes, for this AI stuff, we think about, of course, huge sample sizes and so. And so then asymptotics is maybe more appealing than it was 20 years ago or so, where we had maybe sample sizes of 200 or so. And so I think it's one concept to say something about the posterior. It doesn't say everything about it, but the non-asymptotic bounds are typically quite loose from the vertical perspective, and then one can only do what is possible. Interestingly, I mean, we discussed it also before, for these deep Gaussian processes do have the property that they work better than deep neural networks for small sample sizes. So we know that already from the empirical research, and that gives more vertical backup for the very large sample sizes. Yeah.
Thank you very much.
Good, thanks.
Other questions? Oh, somewhere there first. Thanks. Yeah, sorry. Oh, no. Yeah.
Great, thanks very much. Oh yes. So I really like the fact that you had this hierarchical prior where you kind of had to put a prior over the different graph structure because that basically allows you to infer the graph structure, which you then take advantage of later on when you see lots of data. That's sort of the rationale behind having that in there, right? Now, what I didn't understand is how that related to the asymptotic results for neural networks. So in the earlier slides, when you show these contraction results for neural networks and the fast rate that they get, did the connectivity structure in the neural network need to be matched to the connectivity structure of the composition in reality? Or was that some kind of a magical property that you got somehow during training and you didn't need to specify this extra hierarchical prior on it?
Indeed, yeah. So for the deep neural networks, you don't need to specify that as an underlying structure. So they learn it under conditions. So first of all, the theoretical results that we have is to take the depth in the neural network scaling with log of the sample size. So you need to learn one function, you need already a couple of layers, and so it's a different type. So for one function, for this composition, we would think we need one Gaussian process, and so in this, but for the deep neural networks, it's spread out over a couple of layers. And then we have another regularizing mechanism that is the sparsely connected neural networks that we have. And so that forces the neural networks to concentrate on these compositional graphs if they are somehow, or compositional structures, if they're somehow present. And it's a good point whether one could do that the same thing in the for the deep Gaussian processes, but yeah, I don't think it is different. Yeah, I don't think it works. Yeah.
Thanks.
Yeah, maybe one more question.
Thank you for the lecture. I think that in general, the literature on central limit theorems for neural networks is a very sparse literature. Some of the authors might be here, but my question is, how extendable is this in terms of different types of deep neural networks? You have RNN, CNN, and even transformers, so on. So how extendable is the analysis to different types of deep neural networks? Thanks.
Mm-hmm.
In terms of asymptotics. And
okay, yeah. So I mean, for this first part on deep Gaussian processes, then we really think about some supervised learning problem, and that corresponds a bit like to the feed-forward neural networks, the simplest neural networks. So for the last part on the Bayesian neural networks, yeah, that is all very preliminary work, which is now just coming up in the literature, and so I just wanted to include that here to give a bit of a broader picture on these hierarchical structures that can be learned. Indeed, yeah, I don't think that, I mean, there's certainly no theory on other like time series or so with Bayesian deep Gaussian processes and so on. All this could be done as well, but that would then maybe more resemble the recurrent neural networks, or so maybe you also would try to build in some sort of recurrence into your Gaussian process, deep Gaussian process structure or so, because you want to mimic a bit what the recurrent neural networks do, and then you can extend that. You can go to LSTM networks or even to transformers or so, but all this hasn't been done yet. Yeah.
thanks.
I would like to close the session. Last question, and I'd like to thank Johannes again.
Yeah, that was okay. Yeah.